I'm a researcher here at MSR AI. I work primarily on program synthesis, or more generally on various different ways to combine together your traditional technologies from the good old-fashioned AI, symbolic search, formal logic, ways to analyze programs, and so on, with deep learning, reinforcement learning, neural technologies, and all the advanced machine learning that we have nowadays. Today's lecture is generally an overview of the field, overview of the ways you can apply program synthesis in your products, ways you can benefit from it, all the different applications of it, and that's generally about it. Feel free to ask questions at any point during the hour. We are going to stay roughly at the high level and give you a lot of pointers so that if you're interested in any specific topic throughout the hour, feel free to follow it offline if you want to. Sounds good? OK. So let's start with what program synthesis is and why do we even want to generate programs. Programming is fun. Why automate it? Well, back in the early days of AI, in the 1950s, 1960s, when people assembled and talked together about what do we want AI to be, what this term even is, automatically writing code was one of the problems that they designated as a key feature that we want the computer to be capable of. Back in those days, it basically meant, one sec, so I'm going to turn off the auto switch because you don't want to be going faster than it's necessary. Back on track. So back in those days, that basically meant that we are going to give the computer some sort of specification over what we want our program to do. Like if we want the computer to give us a sorting routine, we're going to say that a sorting function is something that takes an input in an array and produces another array such that it's a permutation of the original one, but it's also sorted. And the idea was that we would write this down, give it to a computer, and it would spit us back a piece of code that satisfies this specification. As many problem specifications back in those days, it was a little too ambitious. And we never gotten to the point where we can automatically write us a web browser or a Cortana or something along these lines. However, modern program synthesis still lives and finds a ton of different applications, even though it doesn't give us applications of the size of a web browser. It looks a little bit different now. So modern day program synthesis has three big components. The first is that it still starts with user intent. Although what we found over the years is that people generally don't like to write logical, complete specifications over what we want our programs to do. Not only you cannot always come up with it in the first place, but it's also laborious. There are other ways to specify intent, like you can give examples of what you want your program to do, or you can, in a natural language, in English, say, describe the behavior of the program. On the other hand, we have the program space. That describes all the space of possible programs from which you want to select one that satisfies your intent. You can imagine it being, say, any program in a general purpose programming language like C# or Python. Or more often than not, we actually write specific, domain-specific languages for particular tasks and purposes and say, pick me a program from this language. And both of these components are inputs to a search algorithm whose goal is to actually find the right program. And historically, that's usually been some kind of search, enumerative or deductive logical search. But nowadays, we also have neural networks at our disposal, and they do this job fairly well, as we'll see in many cases. And out of this combination comes a program. Different projects pick different combinations of these three components. And we will see several examples throughout the talk. There are several applications if you pick of these. So for instance, we can say, well, let's say we want to generate a question, take a question from a user and generate an interpretation of that question as a command and a plan how to satisfy a query. So that gives us a dialogue system and conversational agent. Semantic Machines, a startup recently acquired by Microsoft, has program synthesis technology as a backend from their key conversational system. Another one is, who here is familiar with flash fill in Excel? A few people. Good. So basically, we'll look at flash fill a little bit later. But the idea is, if you have a lot of data in your spreadsheet that you want to clean up and standardize in the right format, instead of writing a bunch of regular expressions yourself, you can give a few input-output examples of what you want the transformation to do. And it will give you a string-to-string program that cleans up your data according to the examples. That's another instantiation of the same paradigm. Or we can go all the way and actually talk about general-purpose code generation, like IntelliSense or autocompletion, if you think about it on the level not of a single token, but more of complete expressions. And there, your intent is what's the context of the current program, and the program space is any expressions in the language that you're programming in. So that concludes the general outline. And in what follows, I'm going to highlight some more applications with particular choices of these components. And we are going to progress through several different ways to satisfy this application and implement them. We'll start with the traditional logical one and cover it at a very high level. How do you take an input-output examples and search for the program? That's how program synthesis has been done historically, and we'll cover pros and cons of this. And then we will talk about how to add more machine learning techniques into the mix and talk about several projects that combine together symbolic implementations of program synthesis and neural ones. Any questions? Excellent. So let's move on. Well, if you're talking about programming by examples, let's start with probably the most famous Microsoft application of it, flash fill. It's a feature in Microsoft Excel that started wide industrial applications of program synthesis. Basically, what it allows you to do is to say, hey, if I have a lot of data in my spreadsheet, and I don't feel like writing the desired transformation of this data all by myself, like in this case, combining the names in the right format, I can just give one or two examples of what I want this transformation to do. In this case, one example given in the second line will suffice. And flash fill will come back and fill in the rest of your data according to the template that it thinks you want. The actual template that it generates behind the scenes looks somewhat like this. It's a program in a specific language of string-to-string transformations. So in this case, what you probably want is something like take the last name, add a comma, add a first name, add a space, then add a substring of the middle name starting from the first character and ending at from the last uppercase character, and then add everything with a dot. Except if you look at it, you'll actually notice that the data is in two different formats. So in order to complete it all, you'd probably want to give a second example. And then flash fill will amend the program and add a conditional to the top based on whether the middle name is present or not. So that's the full program that satisfies the task here specifically in the spreadsheet. Couple things to notice about this. First of all, the program is not in Excel formula language. The program is not in C#. The program is not in BASIC. The program is in a particular language that the designers of flash fill came up with in order to cover the space of tasks that is useful for this feature. String-to-string transformations. A domain-specific language, or a DSL, is crucial for most programming by example tasks. It gives you the expressivity required to cover the space of tasks without making the problem so hard that there is an infinite number of programs in a general purpose language and you have no hope of finding the right one because there's just way too many of them. The general principle that we describe here is called programming by examples, or PBE. That's one flavor of program synthesis. We'll see several more later in the talk. And programming by examples, after flash fill came around into the mix, became widely popular and successful. You can take the same principle and implement it for selecting data from a web page, transforming tables, joining them automatically, transforming data from one JSON schema to another JSON schema, clustering data based on syntactic patterns, lots and lots of different things of the same form. PBE works excellently, but in order to make it work, you have to overcome a few challenges. So you can already see from this example what they are. For instance, like the number one rule, if someone gave you examples, you must satisfy them. That's what the user expects. So at the very next slide, we are going to see how that actually happens. Second, examples are great, but a single example doesn't actually necessarily constrain your problem enough in order to satisfy everything from the first example. Examples are ambiguous. Even in that case, we needed 2 in order to get to the right one. So ideally, we would like to learn the intended program, not just the one that satisfies the examples. And we cannot read the mind of the user, so we need to do something smarter here. And even if we can get the intended program, how do we know that for sure? Because the user can just keep giving examples. How do you know when to stop and say, this is definitely the same program? Your examples don't really change anything. Now, the process that I showed on the previous slide is interactive. It's back and forth communication with the user. Because it happens in real time, you want every iteration of it to be extremely fast. And the DSL design is a little bit of an art. It must be expressive enough to cover the space of tasks, but still concise enough so that program synthesis finishes within a few seconds. So for instance, for flash fill, this is an expert. That's not the full DSL. But basically, it works in layers. You're saying a program is either a single piece or a concatenation of multiple pieces. And a single piece can be either a constant string or a substring of one of the inputs based on 2 positions. And each of these positions is either an absolute position in a string based on an index or a regular expression-based position in a string based on a pair of regular expressions surrounding it. And you can design these, stick more and more operators like that. It's only your imagination, essentially. That's literally what you would write, a context-free grammar of a small language. And if you make it expressive enough to cover the tasks, that will be sufficient. Questions so far? Yeah?
What do you do with conflicting examples?
In this setup, we assume the examples are golden. And if the user made a typo or anything, then you would just come up with an empty set. However, what you can actually do in practice, because that's unsatisfactory, is to synthesize a set of programs from either example alone, and then see if you take out one example, is it possible that the rest of them actually gives you a consistent program? And then that will give you a mechanism to point to the user and say, you maybe made an error in this one. It's not consistent with anything else.
You also need to write a binding to a real programming language.
Yes. So you need an implementation for each of these operators if you want this program to run. In this case, you imagine this is like a couple lines of C#. OK. So how do you actually find the right program? You have a grammar. You have examples. Now, we want a program that definitely satisfies these examples. I'm going to describe the principle in one slide, we are going to make it a little bit more complex later on. So for instance, let's use flash fill as a running example. We start with some specification of the intent. So for instance, we have a couple of these input-output examples. We want this string to be translated to that string and this one to that one. At every point of time during the search, you do the following. So the search proceeds top-down throughout the grammar that I showed in the previous slide. So you're going to be building your program in the order of its abstract syntax tree. If you haven't seen the term AST before, it's basically the tree representation of the program that I showed in the previous slide. So the program that we want here is some concatenation of several pieces. Some of these are constants. Some of these are substrings. Of course, while we are doing this search, we don't know that yet. So at every point of time, we have a partial program. For instance, suppose in this moment during the search, we've already somehow decided that, OK, the left part of the program must be a constant 2 colon space. But we don't know what the right part should be yet. So we start with a hole. This is always some hole in our partial program. Initially, it's just the root. From the previous program, we know that these are the examples that this whole should satisfy in order for the rest of it to satisfy the original ones. And again, initially, that's just the original examples given to us. And I'm going to describe the principle recursively so that it applies at the top as well as at every hole without mentions. What we want to do is the following. First, look at the grammar and say, what possible operators could appear at this point? For instance, let's say we decided that here we also want another concatenation. There are other options. Now we have a program with two holes, a left portion of a concat and the right portion of a concat. Again, we don't know yet which programs should appear in there, but whatever they are, based on these examples, the left one must output A and B in order for the entire program to satisfy the holes. And the right one must output L and O. What we just did is we propagated the examples top-down throughout the program. And you can imagine writing this rule in, again, a few lines of code. This rule basically looks like, look at the output examples that I'm given. I know that the program operator at this point is concat. Now, a specification for the constituents is just split the output string on all possible locations. Some of these splits should give us the right program. In this case, there was only one split if we ignore empty strings, but there could be multiple. So it kind of looks like this, essentially. A couple lines. Yeah?
Why do you want to exclude empty strings?
Just to make the search faster, essentially. In practice, for this domain, it's almost never the case that the right program actually gives you the empty string. And if it turned out to be the case for a specific user task, you can always go back and resynthesize. And this process now continues for every hole, top-down, all the way until the leaves, until you get the full program. So what do you get out of it? First, it's correct by construction. If your propagation procedures are valid and sound, you know that the program that you get out of it must satisfy the examples, at least. If you want it to not just satisfy the examples, but actually be preferred, ideally, you want to incorporate a ranking function that will look at the program and give you some score over how likely this program is to be generalizable. You can machine learn this ranking function. There will be some pointers in the slides. And if you have the ranking function, you can propagate it throughout the whole search process and actually learn top K programs and not just a single good one. And finally, this principle applies to lots and lots of different operators and domains. I just showed it on string transformations, but you can imagine the same for any data transformations, web pages, you name it. I already talked about. The only thing that they need is a way to propagate the examples, essentially invert the implementation of the operator, even approximately. And for many cases, it is possible to write efficiently. Yeah?
It looks like exponential complexity.
Yes. We'll cover that just in a bit. OK. Do you want to apply this principle? We've built a framework in which you can just write down your domain-specific language, write down these propagation rules. They're really short, simple, and it will spit you a synthesizer. So you can build yourself a copy of Flashfill in a matter of hours or days. That's been applied in a dozen different places inside and outside the company for various domains. Many of these domains are already integrated in the framework, so if all you need is just by example data wrangling, that one is available out of the box. But if you don't, basically what happens is that you have a framework which has all these synthesis strategies like deductive search, and you give it the definition of the language, and it generates you a specific synthesizer tailored to this domain-specific language. On top of which, you can now build apps and services and UI experiences, which are the ones that at runtime take as input examples and spit out the programs for the user. OK. I'm not going to return to prose. So if you have any questions at this point, feel free to ask.
Open source? Open source?
Not open source. Open source inside the company. Not open source yet. Yep. OK, so the obvious question was asked right now. It's a great search procedure, but as many search procedures, it suffers from a tiny drawback. It can be slow, exponentially slow. Because at every point, you're going to be splitting your spec into possible cases of how you can satisfy it, and that grows very fast, very quickly. So what do we do about this? Which brings us to the modern approaches to program synthesis that combine the power of two different worlds, statistical and symbolic. So let's talk about making deductive search faster, first of all. What is the issue with deductive search? Well, you have an entire search space with lots of different branches. Unless you can guarantee that some branches definitely cannot possibly satisfy the examples and prune them out, you're going to explore them trying to find the right program. Well, but that doesn't have to be the case. So if you look at any individual problem, you, as a human, can immediately see that some of these branches are unviable, even if they're theoretically viable. So here, it can't possibly be a substring program alone that satisfies this spec. There is a colon in here. There is no colon in the input. You cannot satisfy this with a single substring extraction. You need to concatenate at least something. So if you know this, why can't we teach a neural network to do this? There are two approaches to doing that, one more shallow, another more deep. The shallow one is very simple to implement and train. It's called DeepCoder, if you want to look up the paper. And the principle is simple. We are going to take our examples and feed them to a neural network that will give us a distribution over the operators in the language that it believes should appear in the program that satisfies these examples. And then once we have this distribution, we can look at the least likely parts of the distribution and say, how about we just eliminate them from the search? Because the network believes these paths cannot satisfy the example. And that's essentially it. If you want to train this, the only thing that you need is a database of tasks and programs. Even random ones will suffice pretty often. And from each program, you extract a set of operators and give them to the network saying, this one is present, this one is not. Now, this already cuts out quite a bit and works well. But you can notice that this process runs only before starting the search space. However, the same search continues throughout the entire tree recursively, so it seems like we are not using the opportunity as often as we could. If you do that at every step instead of just at the beginning, you arrive at something that we call the neural guided deductive search, where basically at every step of this way in the search, we are going to take our partial search state and feed it to a network who is going to look at it and reorder the operators and give us a different distribution over the branches at the next step. And now that allows you to cut off another part of the search. And you can keep doing it at every step of the way until you arrive at the right program. OK. Now, how does it actually look technically? What you want to do is the following. So you want to first create a complete data set of intermediate search results. Run your program synthesis without any neural networks or without any guidance. Let it explore all the exponential space. But collect all the results and say, at this search branch, when we had a choice between k operators, and we had this spec of input and output example, we explored all k branches, which gave us back k top-level programs. And according to the ranking function h that we had available, program P1 had that score, program K had that score, and so on. What we want is to pick a branch that will maximize the score of the program. That is the score that tells you the program is generalizable and intended. So we want to learn a predictive model which can take as input a branch ID at this state and approximate how good the score is. to clarify, you don't want to just choose a branch. You want to make use of these scores, because scores are not uniform. They actually have meaning. A score of that range will tell you this is the program that is highly likely, and a score of that range will tell you it's likely but not that much, and so on. So we want to optimize the scores, and we train using the squared error objective over these scores. Which model architecture do you actually use depends on your task. For instance, for strings, you're going to say, I have my input example, I have my output example. I'm going to embed them one character at a time, process with an LSTM for inputs and outputs. And then for each individual production ID, I'm going to feed that to a multi-layer perceptron, which will emit me a program score. That pipeline can be run for each production independently, for each operator, and then you just select the few top-ranked ones. There are some caveats to this process. So the good part is, if implemented well, it guides the search toward higher quality programs, and it eliminates the branches that are unproductive. They don't get you to the goal. The downside, and the thing that you need to be careful of, is that if you choose wrongly at any point throughout the tree, you're going to eliminate the branch with the right program, and you're done. So if you don't want that to happen, you don't want to always pick just the best branch as predicted by this model. You want to pick several of them, and ideally implement something like branch and bound on A star in order to explore a frontier of the search process instead of just blindly picking the best prediction. OK, so that concludes the first approach to combining the search and the neural world. If we go all the way to the sky and look at it from bird's eye view, what basically happened is that we had a completely logical procedure, a symbolic search process, and we found a way to guide it using a neural network. Well, the obvious question is, why don't you just try and learn the neural network in the first place? Turns out that works in certain cases, doesn't work in others, and we are going to see a few examples on how do you design the right architecture of a neural network if you want that to solve the entire program synthesis problem. The obvious downside to just using a neural network is that you cannot communicate the descriptions of all the operators in the program to it. You cannot guarantee 100% by construction that the program that the neural network is going to emit is going to satisfy the examples, and forget about satisfy the examples, is going to compile. So if you want the neural network to be at the core of the search process, you need a way to guide that using the symbolic process. Have a component that tells the network that this is how you make your programs compile, and this is how you make them satisfy the examples. So let's look at how to do that on a few other domains. The setting where this can be illustrated best is the one dear to many of our hearts, which is writing SQL queries. It's been a long-standing dream of the program synthesis community for a long time to have something that can just take a question over a given table and spit out a SQL program that actually corresponds to this question so that you don't need to write it yourself. Turns out, we have, if you phrase it as a machine translation problem of sorts, and implement a standard encoder-decoder attention pointers LSTM that takes as input one sequence and outputs another sequence, there are quite a few things that this architecture already gets right. So for instance, it can tell you that, OK, based on the embeddings of the words, this is word that has something to do with temporal properties. And this column name is also about temporal properties. So maybe this van should correspond to the year. I can tell you that this column contains numbers, so it's ordinal, and there is the word last in here. So last often corresponds to a max operator in this case, based on my data set. I can tell you that this constant appears in the table, so it should probably appear also in the program if it appears in the question as well. These things can be noticed statistically pretty reliably. And if you want details, you can look up, for instance, this paper. So specifically how you implement the sequence-to-sequence architecture in this case is that you have an LSTM that encodes your schema, the column names. You have an LSTM that encodes the question. And then the decoder LSTM at every point can output one of three things. Either it outputs a column name, in which case what you actually want to do is to have a copying mechanism that will look at all the tokens in the column names and have a distribution over them and pick the best one. Or you just output a constant token, in which case you just have a softmax distribution over all the possible constants that appear in your grammar, like an equal sign or an operator max or things like that. Or you want a particular value, in which case that's another copying mechanism that it just looks at the distribution over the words of the question instead of words of the schema. Now, if you implement that, you'll see that it works to some extent, like it gets you 80% of the way, figuratively speaking. However, as we mentioned, it cannot guarantee you that the program that you are generating is actually correct. Now, in this case, we have natural language as a specification, not examples. So there is no way to say, look at the program and check whether it satisfies the spec or not by construction. However, at least we would like us to generate programs that are valid SQL and are likely to be correct and compile and execute. And we delegate to the neural network the job of making this program likely, as in likely to be the one that satisfies the intent expressed in the language. If we want this guarantee to be present there, what you want to add on top of the neural network is something that we call execution guidance. Execution guidance is a lot of post hoc filtering criteria that enforce that the generation of the neural network is a valid program. What does it mean specifically? So let's look at this example. We have a schema, we have a question, we have some neural network that processes all of it, and then one token at a time outputs us a SQL query. However, in practice, as you probably already know, based on the standard architectures of ML and ways to machine translation and whatnot, you don't usually output a single prediction. You implement something called the beam search and output multiple predictions at every step of the way. So as you progress through time during this decoding and generation, you're going to say, give me the top 50 predictions at this point based on their joint probability with the prefix that I've generated so far. Then I'm going to eliminate all but the top 50 ones, and then move to the next time step and also ask for the top predictions, and so on. If your beam width is not 50 but 1, you get the greedy single token generation that actually is pretty fragile because, again, if a single token during generation erroneously has a lower probability than some other one, you will not reconstruct the right program, which is why people implement something like beam search. Another thing that beam search gives us, yeah? There was a question? No. OK. Another thing that beam search gives us is a way to look at these partial programs and eliminate not just the ones that are low probability, but also the ones that are unlikely to be good. So specifically, let's look at some cases in here. OK, there is a sum and there is a city. It's a syntax error. I don't know how to sum cities. If you had this full program, you could give it to a SQL compiler, and it would tell us that cannot possibly compile. But even at this step, you can already look at the partial program, give it to a compiler, and it will tell us this is already a syntax error, so you might as well eliminate that from the beam. Same here. This is not a syntax error. This is technically a valid SQL, but if you try to execute it, it will already give you an empty set. And if, for instance, your SQL dialect doesn't allow ORs, then you know that sticking further more and more clauses on top of this program is only going to make the output more empty. most of the time, the question is actually answerable. So you might want to decide not to output a program whose output is guaranteed to be empty. If you want to allow unanswerable questions, that's perfectly fine. Just don't include that particular filtering criterion. Another instance of this is, so SQL actually, as any language, has a grammar. At any point of time, as you are generating the program, you can look at the last token and say, OK, based on my grammar, I know which tokens can appear at the next position in principle. Like I just generated where, the next thing must be a column name. It cannot be some other operator, whatever. In practice, it means that as you are generating things, you want to do this analysis, come up with a set of tokens that can come at the next position, and then all the other ones mask out of the output vocabulary, give them the mask of -infinity so that the network cannot possibly choose them. That enforces you a very simple way to make the programs compile by construction. This technique you can actually incorporate in training as well, not just in the inference, so that as you are training the network, at every point, you give it a choice only of the valid tokens, not of all ones that are possible in the grammar. That works in programming languages because programming languages have a valid grammar. It's a little harder to do that with natural languages. OK, questions? Another good way to use insight from the programming languages world is, I'm going to illustrate this on the same problem of taking language and outputting SQL or something like SQL. But we are going to talk about sketch generation. So intuitively, when you're writing a program as a human, you don't usually write it all the way end to end, like I illustrated right now. You don't sit down at your computer and say, OK, I thought really hard. This is the right program. I'm going to write it, start talking to the end token, and it's going to be correct from the first attempt. I mean, this sometimes happens, but not as often as we would like. What happens most of the time is that you do that in stages. You write some skeleton of the target program, and then you fill in the holes. And sometimes you go back and iterate on that skeleton and maybe correct some parts that you wrote before and fill in the next holes, and so on. So there are neural network architectures for program synthesis that emulate that process and try to make it more akin to how human programmers operate. And that is surprisingly effective. The simplest way to do that is to split the generation in two stages, what's called sketch generation and program generation. A sketch is a program with holes. It's just, this is the way the program is going to look like as a template, but without any specific leaves, constants, variables that are going to make it a valid program. Like in here, like if this is an expression that I want to generate, this is a function that selects all the flights, that whose departure time is less than that, and it's a flight, and that's essentially it. So remove all the constants and variables from this process, and you get a template. A template is, it's a function that selects all flights whose departure time is less than something. So split your program generation in two phases. The first LSTM will output this sketch, and the second LSTM will condition on the sketch and spit out specific ways to fill in that sketch. There are several different ways to implement that. The simplest one here that I've shown is just have two LSTMs. One will output tokens of the sketch. Another will output tokens of the program. And in cases when the target program actually appears in the sketch, it will just copy it from the previous one. And if it does not, it will generate a new one. So this idea works not just for SQL. This idea works basically for almost any program generation process, as long as you can come up with a particular definition of what constitutes a sketch. OK. Questions at this point? We've come all the way through neurosymbolic. We are approaching the last part of the presentation. No questions. Excellent. So let's talk about neural program synthesis if we don't have the search available to us. Now, some of you may be asking, well, why did we come all this way and try to take the methodology from machine translation and try to apply it to program generation? I mean, there are some similarities, but it's not exactly the same task. And you're right. So it was the perspective of the machine learning community in the beginning to say, well, a program is just a sequence of words. We know how to deal with sequences of words. Let's try to apply the same ideas. And that kind of works, but has a few problems. Like, see, programs are very different from natural language. They have keywords, the semantics of which we know it's well-defined, executable, but it's not known to the neural network. Programs are a lot more sparse than natural language sentences. See, a lot of the identifiers in the programs are only used randomly. So someone came up with them, and they're used a few times in your source code, and that's it. The distribution has a very long tail. The natural language distribution also has a long tail, but not even closely as long. In practice, it means that if the neural network doesn't see enough examples of using a particular identifier, it doesn't know what to do with it. And the programs have a much longer distance dependencies. See, we probably talked about long distance dependency problem in natural language, for which the LSTM was invented, and some other techniques. But a long distance in natural language sentence means what? Like 20 words. A long distance in a program means there is this file somewhere in the other subdirectory that you've probably forgotten by now, but I suddenly call a function from it. So when people realized all of that, try to graduate from sequences of words to trees of words and try to process whole ASTs in order to give structure to the program we are generating. But even that doesn't make use of all the known rich information available in the source code of a program. So the current approach is encode the programs as graphs. This is the one that brings the best of both worlds. What do I mean by graphs? So specifically, we are going to have nodes that correspond to particular locations of a program and edges that correspond to semantic, not just syntactic, relations between the variables in the program and the ways they're used. And I'm going to show that in a lot of detail just in a few slides, so don't worry. The nice part about this approach is that we can run static analysis algorithms like the ones that are present in the compilers that we've known for decades and get all of this semantic information and then embed it so that the neural network can make good use of it and know when the program is executable and if it's executable, how. So let's see how do we do that. We are going to try to analyze or generate a program that looks somewhat like this. Every location in this program, we're going to represent as a node in a giant graph. And then there will be multiple different types of edges that connect these nodes together. What are the types of edges, and what are the semantic relationships that we want to encode in this representation? For instance, the most obvious one is just syntax. This is what you've already seen. So for instance, if you just have a single type of edge called next token, what you will get is a chain of nodes connected with edges that corresponds to a single sequence of words. And that's exactly what an LSTM takes as input and outputs. That's your baseline. If we just add a single other type of edge, the abstract syntax tree child, we now have a representation that has both the sequence relationships and the tree relationships, the AST on top of this. So now this already gives you two different ways to look at the program. its structure and its order in the file. But that's not enough. We actually want to understand what the program does, not just how it looks like. A way to do that is to also add semantic edges from the data flow. So if you haven't heard of the data flow frameworks, what they do is they look at the program, and they come up with some approximation of how the relations between the variables can flow throughout the program if it's executed. Like, for instance, you can say, OK, I'm looking at this variable here right now. When was the last time it was possibly written? And if we are looking here, for instance, well, the last write is probably somewhere around either here or here. I don't know in which iteration of the loop I am right now, so I'm going to add both of these edges. If I'm looking at this location, when could possibly be the last write? Again, either here or here. Just add all of them. Don't try to analyze it on a specific input. This is a generalization of all. Another edge. When was a variable last used? Similar, but just about reads instead of writes. Another one is, if I'm looking at an assignment, from which particular variables is it computed from? And so on. You add them to the same graph, crucially, and now you have a representation that encodes the program as a mixture of both syntax and semantics, which is what we didn't have before in the previous approaches, which looked at the program just as a syntactic object, not as an executable object. Now, after you have all of this, the important part is, of course, how do we process all of this graph with a neural network and actually make any kind of sense out of it? Let's talk about that. So we'll start with RNNs. RNNs were our baseline. So when we had the chain structured data, like text, we processed it using a very simple algorithm, which is we had a chain of so-called recurrent units, a cell that does a computation based on the vectors of representations of individual words. And we process it in a single sequence, saying, let's take the representation of the word, embed it as a message, a vector. And then at each time step, the recurrent unit is going to transform this message, pass it to the next one, who is going to transform it again, pass it to its neighbor, and so on. So an operation at this point is just take your current representation, take the representation passed to you from the prefix, process it, and then pass further. And that continues until the end. That's essentially what an RNN is. You all know RNNs. Now, if we add more edges to this structure, we now have graph structure data, not just a chain. So how do we adapt this computation scheme? Now, there is no simple order anymore. Well, let's look at how to do that. So we are going to start with a graph. And our graph has states, which are locations of a program, which have embeddings, just like words had embeddings. For instance, you could say, take the identifier of a variable and embed it as a word and represent it as a vector. We also have edges. So we had multiple different types of edges, and each of them is going to be also represented as particular recurrent unit. So now we have a structure that has a recurrent unit at each node, just like with text, and representations in this node, just like with text. And we have multiple types of edges instead of just one. So the idea is just you take a node state, and you pass it through the edge network to every neighbor at once. So take a node state, pass it. Do that with every possible neighbor according to that node edge. Now we have more than one message arriving at a given node instead of one, as in the case of RNNs. So we'll need some way to aggregate it. Sums usually work well, but you can experiment with averages or other ones. So, and the recurrent unit, again, takes your current representation of the node, takes the arriving messages from the neighbors, and updates its representation. The structure is very similar to RNNs. It just happens at more than one node, and it happens with more than one neighbor. We do that for every edge type separately, and we do that for every node concurrently. And what we get is a way to take a representation at node and use the information about its neighbors in order to compute it. And if we do that multiple times, unroll the network for several different layers, we now get some processing of a whole program based on the propagation of the messages throughout its structure. OK, so this is about GNNs. Natural question is, what does it all have to do with synthesis? Well, see, what it gives us is a great way to encode the program. And if you have a particular good representation of a program that is able to make sense of its syntax as well as its semantics, you can apply this encoding method to the programs you are generating, as well as the programs you are conditioning on if you have something to condition on. So for instance, suppose that you want to do program completion. You have a particular program, and you want a way to sit down at a particular point as the user is typing and give it suggestions. IntelliSense, but not just a single token IntelliSense. IntelliSense on the level of whole expressions. In this setting, there are no specifications like examples or languages. The intent expression is here's the context of my program. What is the most likely completion of that context? So the principle is actually, now that you saw the encoding, is relatively straightforward. You're saying, let's take this context and encode it using a graph neural network. After we encode it, we get some representation at the whole node. This is going to be a vector from which we start generating our program, and representations of variables around it. And that we will pass to a sequential generation procedure that is going to give us the generated code, like this expression here. The generated procedure is very similar to the deductive search that you already saw. It's just implemented with a neural network instead of the logical search. So essentially, it's going to build the expression top-down, again, top-down, left to right. Just do this using message passing and propagation of a graph neural network instead of the logical derivations. So start here, focus on the whole. We want to select what should be expanded in this whole. We have productions. Like at this point, it could be a minus or a plus or a call of a function and whatnot. Just like in the deductive search in Flashfield, we had productions, but there we expanded all of them. Here we are going to just have a softmax that selects over them. Focus on the next whole, expand it. Now we have terminal node, so a terminal node will select over variables. Add the edges that correspond to the semantics, propagate through them, like the last use edge that looks at the variable node in the context and says, well, where it was last used, and continue the same process step by step, left to right. OK. If you look at this particular setting and apply it, you get a network that is actually surprisingly good at looking at small snippets of code and producing expressions at every point and rankings of them. So for instance, this example you've already saw. Sometimes it's not quite correct. So for instance, here, the right expression appears at the second spot instead of the first one, but the probabilities are not that different. Sometimes it's surprisingly good. Like in this expression, it knows that the right one is a character variable should be compared with some constant. It can't generate you the right constant, but it knows it should be some constant. And so on. So I'm going to conclude at this point. That's a higher level overview of multiple different things. If any of these specific things interest you, here's a good set of links. So the survey paper at the very top is probably the best one for a whole field. And it covers the symbolic sections. It covers the neural sections and many particular projects and applications, depending on the ones that interest you. I encourage you to check out specific frameworks because people have built them to simplify particular ways to apply program synthesis in end-user-driven applications. And Prose and Sketch are the two most popular ones, so make use of them. And there are a couple blog posts that point to more recent research and papers and results if you want to take a look at those. And before we go, I want to leave you with some takeaways over this entire talk. Program synthesis as a whole is a way to generate programs in a particular application domain. And in order to implement that, you need three main components. Define your language of programs, define how you take a specification, and define how do you do in the search. And there are several particular choices for all of them. If your specification is examples, so you want to take as few of them as possible, and you want to do that fast, an enumerative or deductive search usually is a great way to do that. It ensures correctness of your programs, at least with respect to examples, but it's not always the most performant way. So if you want to speed it up, a neural guided search is a good way to do that. For other specifications, where you can't quite use search because you need to make sense of language, or you need to make sense of the context of your program, or other domains in which neural networks are more effective way to encode that, use neural networks, either recurrent ones or graph-based ones, depending on the complexity of your programs. And you give up execution correctness, so guide them using partial program execution or the structure artificially added to the programs in order to ensure that the programs compile. Hints help well. You don't want to just generate any program. If you have any hint about what the program should be, give it. Like if you can write a sketch of the right program, write one. If you have a grammar of the language in which you are generating your program, communicate that grammar to the network. Like, for instance, limit the tokens that are available at each position based on the partially generated program. If you can train a ranking function that can prioritize some programs better than others, that is another hint. And there are frameworks that people have built for particular kinds of program synthesis that you can leverage in different settings. And that concludes the high-level review of program synthesis. And happy to take questions. Thank you. Questions? Yeah.
So can you elaborate on these ranking functions? Because I think you covered like how we do ranking using neural networks on the node level, but not on the program level.
Yeah. So a ranking function is something that takes as input a program, optionally takes as input the task, like what are the inputs and outputs that you wanted to satisfy, for instance, and outputs some kind of score over, hey, this program is probably more generalizable. If you want to train that, what you want to do is build your data set of all possible programs that could satisfy the examples, and then mark them as generalizable or not. You can do that because you usually have more input examples than the ones that are given to the specification. Like in a spreadsheet, in case of Flashfill, you can say, OK, I'm generating the program based on the top 2 rows, but I'm going to judge the programs as good or not based on their behavior on the rest of the rows. And that gives you training data. There are lots of different objectives and the ways to actually set up the learning problem. But what essentially you want to achieve is to say any good program should be higher than all possible bad programs. So the score outputted by the ranking function should separate a good program further from the scores of all the bad programs. That corresponds to something called the max margin loss. Where you say, I want to make the margin between good programs and bad programs as much as possible at the high level. So this is one way to do that if you want to just encode full programs and the tasks, and that gives you a ranking function. You could also do that at every level if you can collect the training data from all the levels of the search process, just like we did with the neural guided search. And of course, if you don't want to train anything, you can just write ranking function. Actually, like some simple heuristics that say programs that are shorter are better, programs that have fewer constants are better, yada, yada, already get you 80% of the way. Questions? Yeah.
Related question. So how do you ensure the performance of the generated programs on the domain they operate? Let's say, would the generated program be a order n squared program, or if it's a SQL, does it take care of the right indexes that are available? Like, how do you kind of build that knowledge into the generation?
Yeah, great question. So I'm going to repeat that because the question is, how do you ensure the performance, as in the speed of the generated programs, is up to the bar? And for different domains, that corresponds to different notions of, say, complexity or indexing and whatnot. OK, performance is another metric on which you want to score the generated program. Like we just talked about ranking functions. The ranking functions are about generalization or applicability of a program. You can build a similar thing for performance if you look at the program and say these operators are, in practice, has slower implementations than those operators. And now, as you're generating, you want to optimize a mixture of two objectives. This is if you can build a simple cost model. For SQL indexes, I suppose, again, you can say, I have indexes for these columns. I know that these operators are more efficient than those operators, and that is a second component to my objective, so the network learns to optimize that in addition to actually generating just the right program. You can also often do that in two stages, where you generate a set of programs that are likely to be correct, and then among those, you pick the most efficient one. Yeah. More questions? All right. Thank you again. And let's get back to coffee.